Well, guess what time it is?
What time?
What time is it? It's time to have a hangout. You know, I have a sound effect today. Here we are at Faraday Studios, and I'm Wizard 4. How are you? And we're going to do our third in a series of 3 hangout with folks from the Royal Institution in Great Britain, NASA, and here we are at Faraday Studios. We're beaming our signal out from Cambridge, Massachusetts. And we are going almost all the way around the planet.
That's right.
People, I guess there are millions of people on YouTube. We'll probably shut YouTube down this morning. There's so many people watching this all around. And my name is Jake. I'm Wizard 4. I actually have a little title. It was given to me by the director of the Royal Institution.
Oh, yeah?
Wizard 4, yeah. Peter Day. It was a long time ago. Peter's an older man. He's older than I am, so you were talking seriously old. About 25 years ago. So I guess this is my silver anniversary as Wizard 4. And I did this silver hair.
Yeah.
To be Wizard 4. I'm the 4th wizard.
Coming out of your head.
And Wizard 1, Michael Faraday. Jacob, get a shot of Father Faraday up there on the board. That's Michael Faraday, and all the folks in London that are watching, they know Faraday very well. I think he's probably the world's first science teacher.
Probably.
Before his day, there was they called it natural philosophy, and he was everybody loves Faraday. So in the honor of Michael Faraday, the Royal Institution, NASA, and here we are at Faraday Studios, we're going to have some fun today. We're just going to hang out. We're just hanging out. So everybody kind of, we're hanging out today, right? Yeah. And I want to introduce the folks that we're hanging. This is really cool. You know, we've got a bunch of students hanging out with us from 3 schools, and then the folks that are watching. But we've got some scientists from NASA, all over NASA. We got people from Langley and Houston and Space Center, Kennedy, all kinds of. Bob Starr. I think he just got out of jail. I don't know. The Bob Starr is producing this thing, right? Yeah. And Kevin Fong, the fellow that if you watch the Royal Lecture, the Christmas lecture at the Royal Institute, Kevin was the guy, and he is cool. He's a doctor. Yeah. He's a NASA doctor, and he's the one that presented the lectures. So this is a follow-up to those lectures. So I'm going to introduce now. Let's start out with Bob, because I just want to. I want you to get over the shock if you see Bob. Bob is our producer here at Faraday Studios, and Bob, you're setting in Atlanta today?
Yes, and I've got space on my brain, so I'm anxious to learn some things today, and I'll be behind the scenes, so this may be the last time you see me.
Is that okay? Well, that's good. That's probably a good thing.
Yeah. That's
good. But you're a good-looking man, Bob. We'll tell you that. But you're a good-looking man. Well, okay. So let's go down some of the scientists that are helping us today. Joya Massa from Kennedy Space Center. Are you there, Joya? Is it Massa or Massa?
Massa.
Okay. Hi, Joya. And who's that with you?
This is Trent Smith with me here.
Well, tell us what you do. Where are you at, and what do you do?
We're both at Kennedy Space Center in Florida, on the east coast of Central Florida, and we are part of the Veggie team here. I'm the Veggie science team lead, the kind of the main scientist in charge of the Veggie program, and Trent is the Veggie project manager.
Yep.
The Veggie is the Veggie? Is that some sort of satellite or something? Do you have a carrot flying overhead? What is it?
Not yet, but that we can build that into the plan.
So you're the guy
on-orbit garden.
Okay, so you're NASA's gardeners.
Well, we enable the gardeners to garden.
Yeah.
You're gardeners. So your garden's going to be on Mars, like in the movie, right?
Eventually.
Eventually. Well, you'll be up there hoeing the Martian soil. Well, that's Trent and Joya. You say it Joya. It spells G-I-O-I-A, but that's Joya.
Yeah.
I learned that. That's Joya. And they're the NASA Veggie scientists. Let's find Karen. Where are you at, Karen?
Hi, everybody. How are you?
Oh, that's Karen Long. Dr. Karen Long. Doctor. Don't forget that. Tell us about where you're at, Karen, and what you do.
I am the manager for NASA Langley's Research Center for the NASA Digital Learning Network. And so our program helps make programs like this possible. And we were able to bring the U.S. schools to this program today. And we're so excited to be able to join everybody.
Well, thank you, Karen. So you'll be answering some questions, too, along with Trent and Joya.
I will do my best, but I'm going to leave the majority of them to them.
Okay. And Dr. Fong is not with us yet, but he'll pop up soon.
No, popped up already.
Yes, he's here.
There he is. There's the man. That's Dr. Kevin Fong, and he was the presenter of the Christmas lectures that kept me just spellbound, and that's hard to do. So tell us a little bit about yourself, Kevin.
So I'm a doctor of medicine. I specialise in anaesthetics and intensive care medicine. I work with one of the helicopter air ambulances here in the UK. I'm actually in Washington DC today. But I also used to work with NASA on and off for about 10 years, working with their life sciences directorate, I guess. Human Adaptation and Countermeasures Office, I think, was the title of the office. So yeah.
Is that all?
That's all I'll admit.
Yeah, all right, Kevin, and thank you. Man, this guy is a workaholic. He's flitting around the planet, and he stops. So I hope these young students that are watching understand that's an excellent group of people that are pausing their day just to share with us at our hangout. So this is really a wonderful experience. I'm buzzed. Oh, we can't forget our friend Olympia at the Royal Institution. Let's find Ollie. Are you there, Ollie?
I am, yes. Hello.
Yes.
I'm in the Royal Institution today, upstairs in one of the offices. And the Royal Institution is a science charity that has been around for more than 200 years, making people think more deeply about science. We have run the Christmas lectures for about 190 years, and we're delighted to be working with Kevin Fong this year to explain how to survive in space.
Yeah, he's smart, isn't he?
He is. I mean, he's got his downsides, but yeah, he is smart.
Well, send me notes later on those downsides, because he's so good looking.
Yes.
I just can't stand the man.
Venom's me too. Yeah.
Okay. Thank you. Now, I hope your kids don't think we're serious. Oh, we're all the time serious scientists here, aren't we? We're all serious, but we're hanging out today.
Yes.
So since we're hanging out, we can be a little flippant and have some fun with each other. Well, let's go. We've got 3 schools joining us too, with some really good-looking and smart kids. Let's go to Arlington, Virginia, back across the ocean to K.W. Barrett Elementary School. And Lori Sullivan, are you there, Lori?
Hello.
Oh, there's Lori.
Hi. I'm letting the kids run the show.
Oh, yes. That's good, Lori. Well, thank you. Well, and so tell us something about Barrett Elementary. What can you tell us about the school?
Well, we are a NASA Explorer school, and NASA picked Barrett as the first elementary school in Virginia to be a NASA Explorer school. So we've been in partnership with NASA for 10 years now.
Really?
Mm-hmm.
That's a neat-looking classroom. If you get the kids out of there, it would probably really look good. So I like that classroom. Sweet. Well, we're going to come back to you in a minute and have you ask some questions, okay? So you get your questions ready. We'll be right back.
All the kids want to say hello.
Say hello.
Hi.
How you doing? Man, that was exciting there. It must be early. It's early in the morning there. Okay. Okay. Hey, we're going to go farther down the coast. We're going to go down to Winston-Salem, North Carolina, to Wiley Middle School. Elizabeth Moore.
Hey, Mr. Wizard.
Oh, there you go.
How are you?
Well, I'm old. That's how I am, but you know, what are you going to do? I'm Wizard 4.
It's just a number.
Just a number. Age is just a number. So that is a good-looking group. Is this a middle school? Okay.
Yes, sir. We have an official introduction for you if we can show it real quick.
Okay, let's do it.
Go ahead, girls.
Hi, we are Wiley Magnet Middle School in Winston-Salem, North Carolina.
And we'd like to say welcome to Winston. All right, everybody do it. Woo!
Here, I'm going to get in on this. There we go. Welcome to Faraday Studio and the Hangout. I like those kids. They look a little ornery. You know, they're a good-looking group. Well, thank you. We'll come back to you in a few minutes and have you ask some questions of our scientists. And last but certainly not least, we're going to go all the way across the Atlantic again to London, to the Ryburn Valley High School in the UK. I don't know if they're in London. We'll find out where they're located. Let's see if we can. There they are.
We're in Yorkshire. Go on, Tom. You stand up.
Now, where'd you say you're from?
Yorkshire.
Oh, Yorkshire. Okay, sure.
Hello, we are students from Ryburn Valley High School. We take part in an after-school club called STEM, where we do lots of fun experiments, such as building our own wind turbines. We are also the winner of a science competition against other schools in Calderdale, but this is by far the most exciting project we've been part of. Hello, everyone.
Hello.
Oh, they've all got ties on. Oh, I don't feel underdressed. I don't have my tie on. That is a good-looking class. And that's a sign. Oh, here we go. I'll just hold this up here. Does that look better? I got my tie on now. Now I can talk to the British kids with some authority. Okay, no, never mind. Thank you very much. Well, thanks for coming all the way across the waters to join us on this hangout. And I hope we do some other stuff together down the road. We'll just keep connecting every once in a while. That's a science school.
That's a science school?
They like to blow things up over there.
Oh man, I should have gone to school there.
That's right. See, he's shaking his head. Yes, we like to blow things up. That's a good school.
Yeah.
So, well, let's get started with our NASA questions. I'm ready. So let's go back up to the Barrett School, elementary school, and they're going to ask the first question. Let's see what their question is and who can answer this question. Let's switch it. Barrett, are you there? Lori?
Hello, we are here. We're turning our lights back on.
Okay, here's the question.
How do tardigrades evolve such strong DNA, and how are they able to survive in so many environments, including space?
Those tardigrades. Now, I got those when I was a kid. I got tardigrades.
I think that's chicken pox.
Oh, that's a different thing.
Yeah.
Tardigrades. Those are the little things. So who at NASA can talk about tardigrades and how they survive?
Well, that's a really good question, and so we know a little bit about tardigrades, but sadly they're not plants, so they're a little bit out of our area of expertise. But they are very amazing, and you can freeze them down to -80. I think you can take them up to about 300 degrees Fahrenheit, and they just won't die.
Yeah.
And I don't know if we actually know why they're able to survive in that fashion.
Yeah, I think it's more than just their DNA. I think their DNA isn't vastly different from other folks' DNA, but they have other aspects of their bodies that are very resistant to things like extremes and radiation and even microgravity and space. They did survive outside in space, but it wasn't a huge number of them. So it wasn't like they all survived microgravity and being outside in space. But they're a really interesting organism, and I think people are doing a lot more research on them because they're just, they're very puzzling. Yeah, they're called microanimals. One of the things that I learned about them that was kind of interesting is they are not technically what we call extremophiles. So extremophiles are organisms that actually thrive in really extreme environments, like the bacteria that might live deep in hot springs or at the bottom of the ocean encased in ice or whatever. So these are not, they don't thrive in those environments, but they will survive those environments.
Right.
But extremophiles are the types of organisms that, we may find on Mars. If we go to Mars and, we actually get to search, there is water on Mars, and there could be organisms that live there that can survive, underground, protected from some of the harsh UVC radiation and other UV radiation that is hitting the surface of Mars. And so it'll be really, really fascinating. And you guys are, the right age. Yeah, you may be the one who gets to go to Mars to look for these organisms. So how cool is that?
That's sweet. Tardigrades. Well, I'm glad. And see, those scientists at NASA are so smart that's outside their field, but they could pretty well answer the question.
Yeah,
I'm amazed.
Quite a bit about the extremophiles.
The extremophiles.
I think Kevin's got a response too.
Oh, Kevin.
So there's a few things. So they have got an amazing DNA repair system. So they're much better at repairing their DNA when it gets damaged than you are, which accounts for their ability to withstand very, very high doses of radiation. As you heard there, they don't thrive in extreme environments, but they can tolerate them. And one of the tricks they pull off is they sort of go into this hibernating state. It's called the ton state, where effectively they just shut down a lot of their bodily processes. The thing that's most vulnerable about you in these environments is that the chemical reactions and the processes that are going on that keep you alive tend to shut down at the extremes of the physical conditions, so very high temperatures, very low temperatures, very high pressures, etc. And they're able to basically do everything but die to keep themselves running on sort of, you know, standby mode, as it were, for ages before they perk themselves back up and wait for better times. So what they're really good at doing actually is shutting their bodies down when times are hard, so that they can get ready to come out of this sort of, it's more than hibernation actually that they go into, but come out of this state when they're when things get better for them. That's their trick.
They're just kind of like bears that crawl in a cave and hibernate, but they do it in all sorts of conditions and survive.
Yeah, exactly that.
That's great. That's a great question and good answers from NASA. Okay, Bob, we're going to go over to Wiley Middle School, and Elizabeth Moore's kids have a question for us, I think. Winston-Salem.
For how long does the suit provide oxygen and 2.6 atmosphere pressure?
So those suits, how long do they provide pressure? That's a good question. How long? Anybody know? Don't want to run out of pressure.
So I think I see Kevin talking, but it's muted.
Yeah, no, sorry, I was on mute. So those suits are very interesting. So you can't blow them up to a full atmosphere of pressure. So at the moment you've got 1 atmosphere of pressure around you. The reason you can't blow those suits up to a full atmosphere of pressure is for a number of reasons, mainly because the suit becomes very rigid and then you wouldn't be able to move inside it, so that's bad. And the other surprising thing is that that you can keep those suits at that pressure for as long as you like, actually, because they've got little refill stations on the outside of the space station, so they can go up and recharge their oxygen. So oxygen isn't really a problem for them. The big problem with spacesuits when you're out on a spacewalk is the carbon dioxide absorbing units. That's the limit of how long you can stay out on a spacewalk. So you can go and get a refill of oxygen from any one of a number of ports on the outside of the space station, but you can't recharge your carbon dioxide absorbing device. So there's a device in your suit that absorbs the carbon dioxide, the waste gas that you breathe out, and it stops it suffocating you. When that thing runs out, you've got to go back inside. And that's usually around about 6 hours, about that sort of 6, 7 hours, I think.
Sweet. I didn't know. And so you can actually fill up. You can fill up with oxygen on the outside of the space station.
Yep, you can get a refill. So I used to think you had to go back in. You know, it was like scuba diving, so that when your oxygen tank ran out, you had to go back in. That's not the limiting factor. It's how much carbon dioxide you can absorb.
Oh, okay. Well, that makes good sense. When you get too much CO2, you've got to go in and drain it out, I guess. Okay, that's great. Let's move to Ryburn. I want to go back to the UK and talk to those kids with the beautiful ties. They've got a question. There you go.
If we go and live on another planet, how will we grow our food? Will all plants grow in space?
Could you say that one more time, please?
If we go and live on another planet, how will we grow our food? Will all plants grow in space?
Oh, there we go. That's a good question for our veggie scientists. How are we going to grow our food if we go to another planet?
Yeah, I turn it over to Dr. Massa.
That's a great question. And in terms of, what plants and will all plants grow as well. Right now on the space station, we are just looking at growing salad-type crops, things that you could pick and eat fresh, because we don't really have any way to cook our food on space station. Now, when we go to another planet, we will probably have some way to cook. We'll probably bring at least something like a microwave.
Yeah, hopefully a microwave.
Yeah. As we go farther, as we're there longer, maybe we'll bring some of the other equipment that you might need. So how we would grow it, when you have a little bit of gravity, it makes things a lot easier, right? On space station, it's actually very tricky because the water and the air, kind of form a ball of water with air inside. And if you think about plant roots need both water and air. So it's really challenging. But when you're on another planet, you have gravity, so it's actually much easier to water your plants, to get enough water and air in the root zone. You can use techniques like hydroponics. You can use substrate-based techniques. So they're
kind of like what they did in The Martian,
like
right?
what they did in The Martian. There are a lot of options. Yeah, you still need a lot of light. Plants everywhere will need a lot of light. But generally, if you give plants the environment that they need, and we think of these 5 cardinal factors. You've got your temperature, you've got your water, you've got your atmosphere, which plants need both carbon dioxide and oxygen. You've got light, and you've got your mineral nutrition, your fertilizer. If you can get all of those environmental factors correct, or within certain ranges, then plants will grow just fine on any planet. We have tested plants at low pressure. It was very interesting to have that question about low pressure. You can actually grow plants at kind of a lower pressure than you would here on Earth, and they will survive, which might be good for a habitat on Mars, so you don't have to make your walls really, really thick.
At 1 atmosphere.
Right. But what types of plants? I think we can grow almost any type of crop that we would grow here, but generally we look for plants that are very compact. High yielding, because we're not going to have a lot of space to grow plants. And you see that in The Martian. The plants are really widely spaced apart. Probably we're going to be growing really dense
shelves, maybe.
Yeah, layers of plants with electric lights, like LED lights. We're probably going to be burying them under the ground to protect from things like galactic cosmic radiation and micrometeorite impacts and things like that, or have really thick walls. So we probably won't be doing it on a greenhouse on the surface, because there aren't that many materials that would withstand, some of the real harsh UV, and then would protect the plants and the humans. But I think we can grow a very balanced diet. We can have things like wheat and soybeans and rice and peanuts,
potatoes,
and sweet potatoes, and all our salad crops. And then we'll have to bring things like a flour mill and a bread machine and things like that along with us. But
you can think of it as kind of a phased approach, where you have things that you can eat, pick and eat. Then you have things that maybe you could cook with a microwave, like a potato or a sweet potato. And then down the road, as Joya said, soybeans, dwarf wheat, things like that, where you process it and make things that you would make at home.
And you're not just making food. That's another thing to think about. Remember, plants are doing photosynthesis, so they're also going to be recycling your atmosphere. All the carbon dioxide that the astronauts are breathing out, the plants will take that up and they'll generate oxygen. And they will also be transpiring the water. And the water that comes out of plant leaves as water vapor is totally pure. So you could collect that and you could use it for drinking water. And you could water them with water that you wouldn't want to drink. And they will be like stills. They'll distill that water for you, essentially. So
those are added benefits. Not only will you supplement your diet with fresh, nutritious food, but they'll help you with your atmosphere and water.
Well, yeah, that's great. Hey, Trent, you mentioned potatoes, and then you said sweet potatoes. Does one type of potato grow better there?
Yeah, I think sweet potatoes are kind of an interesting crop, because they have I think they have more vitamin content. I really defer to Joya on that one.
Yeah, sweet potatoes are a really pretty cool crop. They're in the morning glory family. If you guys know about the plant families, they make these long vines and they have flowers that look like little morning glories. They're very pretty. But the cool thing about them is they are a great storage of starch, but they also have more vitamins and anthocyanins, antioxidants. And then they also, you can eat the leaves and the stems. You can actually eat them as a salad green or as a cooked green. So you can eat a lot more of the plant, which is pretty nice. Potatoes are a very high yielding crop, though. Potatoes are a great crop to grow, and you can get a lot of calories out of potatoes. But, they get a little boring if that's all you're eating.
All right, it's good to know. I didn't know you could eat sweet potato stems. I had to go all the way to NASA. to find out.
We're here for you.
And it may not be every variety, but some varieties you can.
Okay, that's great. Okay, let's go back to Arlington, Virginia, to Laurie's class, and see if they've got a question for us.
Yes. What happens when astronauts get radiation sickness in space? Can you wait it out like a cold, or do you have to go back to Earth as soon as possible?
Oh yeah, Kevin, tell us about radiation sickness. What is that? An emergency?
Kevin, you need to unmute your microphone.
Mute again. Sorry. Right. So radiation, big hazard for space flight. So the problem with radiation is it can damage your body in a lot of different ways. If you get a big dose over a very short period of time, one of the first things it does is it just burns you. So sunburn, when you go out there, if you're silly enough to go out in the sun without any sunblock on, you'll get a kind of radiation damage. You're just getting the heat damage, the thermal damage from the radiation. And that can be enough, actually, if you get enough radiation in space, to be very damaging to your health. And then you get other problems as well. So you get the problems that these radiation puts a lot of energy into your body, and it can damage your body not just on the surface, but at the level of the molecules that make up your body, and particularly your DNA. Now, your DNA is the molecules that are present in nearly every cell in your body that has the instructions for how you make other cells, right? So the reason that you can grow new skin or grow new hair or anything else in your body is because you've got these instructions inside your cell that tell your body precisely how to make the new cells, right? Now, if that gets damaged by radiation, the new copies you make aren't very good, so you get problems, and that's why when people get very bad radiation sickness, they get problems with bruising on their skin and sores on their skin. That's why their hair falls out. The lining of the gut gets interfered with, so that's why they feel sick and they vomit sometimes. So no, you can't wait it out. You're in big trouble if you get a big dose of radiation. And then, of course, there's problems in the long term. If you've had a small amount of damage to your cells through radiation, it puts you at a higher risk of developing cancer later on. So all in all, radiation, really, really bad for you, best avoided. Difficult to avoid in space because we don't have a lot of the protections we have and take for granted here on Earth. Right now, you and I are sitting here, we're protected from radiation because of our thick atmosphere that absorbs a lot of radiation, and because of the magnetic field of the Earth, which catches some of the really highly charged and high energy particles and stops them getting to us. But right here on Earth, really mostly you don't have to worry about radiation, but you should all wear decent level of sunblock, sun cream on a sunny day.
Thank you, Kevin.
Thank you.
All right, thank you. Let's go back to Winston-Salem, to Wiley School, middle school. Here we are. Here they're back. We have a question.
If you break a bone in space, will it have the same effects on your body in space as on Earth?
Ah, breaking bones in space.
So that's a really good question. I should take this, I guess. So as I'm sure you know, your bones do waste in space. Your bones are very clever tissue. It knows how strong it needs to be to deal with the stresses, to deal with the forces that you're putting on it here on Earth. It's why you guys who are at school there, it's why it's so important that you do lots of good exercise when you're young, and because that teaches your body how to lay down all the bone that it needs for the rest of your life. So right now, your body's trying to decide how thick to make your bones for the rest of your life. And so the more exercise you do now until you're about college age, the better and the stronger your bones will be forever. When you go into space, your body says, well, I don't need to carry so much weight anymore, that this guy or this girl is weightless, and the bones become thinner and weaker. And because of that, they're at higher risk of breaking. And we've seen really, really quite high levels of bone wasting, loss of bone in our astronauts when they fly. Now, fortunately, none of our astronauts has ever broken a bone in space. and it's unclear what would happen actually if that did happen. Once a bone breaks here on Earth, what we do is we set it, we pull it back into the right shape, and we set it in a plaster cast, or we do some surgery to fix it into the right shape, and then we let the bone grow back together again. But in space, we know that the healing process, certainly for skin, doesn't work quite as well. I'm not entirely sure what would happen with bone. I don't think anyone is for sure. So it might be a problem. So the best thing is to try not to break your bones in the first place. Prevention is always better than cure, even in space. So it's one of the many questions we have that remain to be answered, although I won't be volunteering to go into space to have my legs broken anytime soon.
All right, thank you, Kevin. You're not going to volunteer to go up, Kevin, and break a bone for science?
Well, actually, to be fair, if I got to fly in space, I might, to be honest. But,
oh, that's good. That's good. That'd be a good reason to go. Okay. Well, thank you, Wiley School. Let's go back across the ocean and see what's going on in Izzy Monk's class. I want to hear this question.
If it could grow plants on other planets, would that mean that it would change the planet's atmosphere like it did on Earth? Would Mars have the right conditions to do this?
What? Now say the first part of that again. It was a little blurry. Could you say it again, please?
If we could grow plants on other planets, would that mean that it would change the planet's atmosphere like it did on Earth?
Okay, thank you. We need to go back to our veggie folks, huh?
Yeah. So, I mean, it's a great question. You know, in the near term, we're really only planning on growing enough plants to support the astronauts, and that would be in some kind of a habitat. So it wouldn't be affecting the atmosphere of the planet directly. But if you start to think about long term, things like terraforming, then you would be able to use biology to affect, you know, the atmosphere on a planetary size object. Now you've got to think Mars is farther away from the sun, so it's getting a lot less light. I think is it around
40? It's 40% of the light. Yeah. You got 1% of the atmosphere. Mm-hmm. You have perchlorates in the water. You have you know, you have very little micronutrients for the plants. So you'd really probably have to come up with something that's a GMO or maybe kudzu. That nothing seems to kill that stuff.
Well. Yeah, I mean, you would probably start with other things first. You'd start with bacteria. Right. You would start with maybe things like lichens, algae, maybe some fungi, and then, you know, as things changed over time, you might be able to
start introduce
more hardy, you know, genetically modified plants, perhaps, and more hardy plants, things that might live on the tops of mountains. But those aren't real productive. So if you wanted to change things quickly, then you would have to probably get into gene modification. Right. But it would be a challenge, you know. We're still not sure.
It's just going to be a challenge, I think, to feed our astronauts to go to Mars. So of course that's our most immediate need, and that's a great question, and that's, I think, a really maybe 100-year question, right?
Yeah, or thousands of years. Right. You know, it could be a very long time, and you know, then there are other questions. I mean, I think we might want to think about it before we go to do any changes to planets. There's rules in place called planetary protection, because we don't know what's there right now. You know, we don't know if under the surface of Mars there are organisms.
A whole ecology, right?
And we don't want to wipe those out just by introducing a lot of Earth organisms. So I think, you know, first things first, we got to get there and check it out.
Right.
That's good about not messing up the local environment by putting our stuff there.
That's right.
You know, I think that's good, because I'm sure I have dandelions in my yard, and I'm sure somebody came from outer space and put those dandelions there. They keep coming back. It's hardy. That's great.
I don't doubt that for 1 minute.
That's what I'm thinking. And kudzu, too. Kudzu came from Venus. You know this, right?
Tell you what, that stuff's hard to kill.
That's hard to kill. Okay, let's go back to Arlington. They've got another question, I see. Arlington, Virginia.
How about mixing water, lead, and tardigrades together to make a shield to block the radiation in space?
Oh, this is like a homegrown recipe. So you want this is great. Tardigrades and lead. All right now.
So that's probably a good one for Kevin, but I can also take a crack about describing. Kevin mentioned the highly charged ions that galactic cosmic radiation is, and really you think about protons, carbon, and iron zipping through the universe at half the speed of light. And what happens is when that impacts lead or other materials which have a nucleus, it can break that nucleus up and you get secondary particles. So you can think of it like a galactic cosmic radiation as a rifle bullet, and then if it hits another molecule, another atom in the nucleus, then you kind of get this shotgun sprawl. And that can actually make things much, much worse for the astronauts inside. That's why oftentimes when we look at shielding for spacecraft, for at least deep space, we look at what we call low Z materials. These are materials that are made of atoms that have very low atomic numbers. Hydrogen, and hydrogen can't be broken. It's just a proton with an electron. So that if a galactic cosmic radiation were to hit hydrogen, it helps take some of the energy out without causing more sprawl. And Kevin, did I get that close?
Yeah, no, absolutely. In fact, it's a really good thought, your thought about a shield. Water is one of the substances that probably avoids some of the problems that you've just heard about. That's called secondary radiation. So, it's not enough to stop the incoming radiation. You've got to stop the stuff that happens because it's effectively broken the molecules and the atoms and the shield you've got, and they're not going to shower onto you. So they have talked about using water as the main component of a shield for a crew on their way to Mars, and they talk about perhaps having an area of the ship had a water jacket around it. You could draw on that water to drink and for all the other things you need water from, but it's a place that you could go and take shelter in if there was a particularly large amount of radiation around, the sort of radiation that comes with a solar flare. So everything you've heard is absolutely true, and it's a great idea to use water. You don't really need the tardigrades in there, and the lead is too heavy. So the lead is too heavy, and it has all those problems of the atoms of the lead will split apart and shower you with secondary radiation as well. So water is a great thought, but you can save yourself some weight by leaving behind the lead and the tardigrades.
Thank
lead's
you.
Lead's a little dense. But if you ever mix that up, maybe we can make a biscuit out of tardigrade and lead. I don't know. That might be a good cookie or something to eat or something like that.
No, lead cookies are very bad for you.
Yeah, I know. Well, that kind of leads us to our next question from the folks at Winston-Salem, talking about affecting your head. Don't want any lead in your head. So let's go to Winston-Salem and see what their question is.
Does being in space affect your electrical brain signals?
What happens to your synapses and such in space, Kevin?
So, really excellent question. So I don't think, to my knowledge, the actual rate. So your body is made up of, or at least the electrical system that controls your body, your central nervous system, and then the peripheral nervous system. So you can think of that as like the wires that lead away from your brain and connect to the rest of your body. All the information that goes up and down them, so the stuff that goes from your fingertips to tell your brain that you've touched something hot, and the stuff that comes away from your brain that moves your arms and legs and that sort of thing, that stuff moves along sort of biological wires in your body. And to my knowledge, I don't think that how fast that stuff is, those signals travel, is affected by space. But nevertheless, when you talk to astronaut crews, they tell you that when they go to space, it feels like it takes them twice as long to do everything. They call it, they refer to it as getting the space stupids, because they feel like they're clumsy and they can't do anything the way they used to do it on Earth. And that's not because the signals are traveling around their brain more slowly. We don't know actually why it is, but it's probably because in space stuff doesn't happen the way you're used to it happening. So the physics, the laws of physics are the same, but the physics of your environment have changed. So when you reach for something and you knock it, it behaves in a slightly different way, well, a very different way than it would on Earth. And there's one other thing, and that is that when you're in space, your the system that controls your eyes and the way it tracks moving objects is kind of messed up. So if someone throws a ball at you and you look up and you see the ball, you track the ball coming towards you, and then you catch it. In space, that action, being able to look at something that's moving towards you, track it, and then do something with it, takes longer to happen. It takes about 100 milliseconds, 200 milliseconds. So about a tenth to a fifth of a second longer for you to just simply do that thing that you take for granted, which is to track a moving object and then grab hold of it or do something with it. And they think that might have something to do with it, because if every time you look for something else it takes an extra tenth or a fifth of a second, then you can see how that will build up over time, and it will make you feel like you're doing things more slowly. So in answer to your question, no, I don't think that the signals travel less quickly around your brain or around your body, the electrical signals, but I think that you feel like everything's happening more slowly because it's a very strange environment, and the way that you track moving objects has changed as well.
Well, thank you, Kevin. That's great. So I'd be a good baseball pitcher in outer space, wouldn't I?
Yeah. There are limits to what space can do for you.
That's what it could do. Slow down the batter or something. Well, I guess he'd be changed too, wouldn't he? Okay. Hey, how about Ryburn? Are you still there? I want another question from Ryburn School.
What are the biggest risks of a manned mission to another planet?
What was the biggest risk?
Of a manned mission to another planet. Yeah. So the rocket scientists I used to work with at Johnson had this saying, and they said that the two hardest things in all of human spaceflight, two hardest things in all of spaceflight and all of rocket science are starting and stopping. And that's still true. So the most dangerous bits of the mission are the so-called dynamic phases of the mission. The dynamic phases are the bits of the mission when the most stuff is moving and happening, and that is launch and landing. And that doesn't matter where you're launching from or where you're landing at. So if you're going to another planet, the most risky thing is the point at which you're launching off the Earth. You're releasing a lot of energy in a very controlled fashion, and it takes great difficulty to do that. That's what makes rocket science. And so that's the riskiest bit. And then as risky, again, will be your arrival at Mars. So when you arrive at Mars, if you're going to Mars, say, you'll arrive at about 13,000 kilometers an hour. You'll hit a very thin atmosphere. Mars has got a very thin atmosphere. You can't slow down the way you would on Earth by using just the atmosphere to slow you down. You can't use ordinary parachutes because the atmosphere is too thin to slow you down. So you've got to have some pretty crazy schemes to slow you down safely enough for you to land on Earth. And that's risky because all that energy that you acquired when you launched, all that energy that you took on board when you launched off the Earth, you have to now lose again so that you can come to a standstill on Mars. And so there are lots and lots of hazards for your human body in space, but starting and stopping and managing the enormous energies involved in those events is by far and away the riskiest thing.
Hey, takeoff and landing. That's just like flying an airplane.
Yeah.
Yeah, that's the dangerous time of flying. Absolutely, yeah. That's a good question.
One kind of additional thing to think about too is if you want to come back from Mars, here we have hundreds, thousands of people working to get the rockets ready, safe to launch for liftoff. If you want to come back from Mars, it's going to be you and your 4 crewmates. The rocket may be there, but to get back, that's a lot of work for a small number of people when you've been there for a while, been doing things.
And the machinery's been there on the surface for some period of time, so it has to work.
Yeah.
So the reliability has to be there and the redundancy. So I think Kevin's absolutely right. Those dynamic phases are important.
Critical. Yeah, it's a scary thing to think about. If you're the one who's launching yourself back too. And I had never thought of that, and then I heard an astronaut presenting on that, and he pointed that out, and I was like, wow, I never thought about how many people we have doing it from this side versus how many they'll have from
on the flip side.
And then you're coming home, and and you know, you really want to be home, but you still have a long journey ahead of you, so you got to keep your morale up, your spirits.
Right.
So I think the psychological aspects of it are another really big challenge for everybody.
Goodness sakes, I'm gonna take my application back. I don't want to be an astronaut. No, I have to eat sweet potatoes for a year on Mars.
Oh, I think.
And then you got to fix the thing and then ride. I don't want to do it. I'm just, hey, tell the folks I cancel out on that application. Okay.
We'll pull your application out. Don't worry, we'll get it right out.
Okay. Thank you so much. Everybody will sleep better here. Okay. Well, hey, listen, Lori in Arlington, do you have any more questions ready? I think we got a little more time.
We have a student that was writing some notes during the program.
Okay, we get one more. We can get one more from your school.
Hello. We thank you for talking with us this morning.
You bet.
We did watch Dr. Kevin's lecture and we loved it. We also liked learning from the NASA Veggie team. And Mr. Bob is behind the scenes, isn't he?
Yeah, Bob's around here somewhere.
We like his funny space brain.
Oh, do you? Well, I have him do another one for you.
There he is.
You better believe it.
There he is.
There he is.
Mr. Bob, we're going to get a picture of you. All right? Smile.
You look like you're psychic.
Okay.
Thank you, everybody.
All right. Well, thank you. Thank you. And we'll be in touch with you again. Would you like to do another hangout with us?
Yes. Sure.
Okay. Well, you're on, because we'll be doing it on a. Somehow we're going to do it. We're going to do another hangout. I like this guy. What's your name?
Quillen.
Thug? Did you say
Quillen.
Thug? Cortland?
Quillen.
Oh, Quillen. Quillen. Okay.
Don't worry if you can't pronounce it. No one can.
I heard Thug. Thug is. Now, we're going to call you Thug from now on, because that's the way it came across the NASA. Okay, Quillen. Thank you.
Thank you.
You hang on. Hey, Thug or Quillen, I'm going to do a couple of activities you can do in your classroom in a minute. Okay, so hang on. Don't hang up. Let's go down to Wiley School, Wiley Middle School in Winston-Salem. Do you have another question?
Yes.
Okay.
How do the space stations provide enough oxygen for a whole year? And
a year's worth of oxygen. That's a good question.
Well, I can speak to that. Here at Kennedy Space Center, we actually, since we quit flying the space shuttles in 2011, over in the space station building where Joy and I work, we have another team which actually has these composite overrack vessels where we actually send up pressurized oxygen.
Big tanks.
Big tanks of oxygen fly up in the SpaceX and orbital vehicles. Those are our cargo delivery vehicles that go to space station. As a matter of fact, we got a orbital vehicle ready to go fly at the end of the month. And the SpaceX 8 is going to go fly at the beginning of April. So we got a couple cargo deliveries coming up to space station here. And inside the capsule, we have tanks of oxygen.
And it's compressed.
And it's compressed, right. It's not liquid oxygen, it's compressed oxygen. In addition to that, they have a means to scrub out the carbon dioxide that astronauts are breathing out. And typically what they'll do is they'll take those their ceramic or oxides, and there's some new technologies they're testing out, but they'll absorb the CO2 and then vent that CO2 out to the vacuum of space. And then, of course, all the water is recycled. And it was pretty interesting. I think recently they discovered that the water recycling was not as efficient as they thought, at least with the urine. And as Kevin talked about, your bones, the way that you build your bones in space is different. And when you go up with lots of bones and your bone density drops, well, where's all that calcium go? Well, it turns out the astronauts actually pee the calcium out. And when you're trying to recycle the calcium, or recycle the urine for water, that calcium kind of gummed up the recycling system. So our scientists at Marshall Space Flight Center actually have a fix for that, and they're going to try to test that and get that back up to speed. And I want to check with Kevin to make sure, did I get that pretty close?
Yeah, absolutely. The problem with calcium getting into your urine is a big deal because it causes other problems. It causes your bones waste, that calcium ends up in your bloodstream, and then it ends up in your urine. So you can get kidney stones with that, which are very, very, very painful. You need a surgeon to sort those out. You get constipation with that. You also get psychotic depression, all of which are really bad for astronauts. So yeah, recycling water is a big problem. When I first went to NASA in I guess '97, there was a guy there called Doug Ming. I don't know if you guys know him, Joy and Trent. And he was about growing plants in a very sealed chamber to try and see if you could support people. And I think back then, and Trent and Joy will know more, he was growing wheat plants to try and generate oxygen. And they had an experiment where they'd shut people in a chamber and they were trying to make a regenerating life support system, kind of like the way we have on Earth, growing your plants, generating your oxygen, scrubbing out your carbon dioxide. It was very exciting, actually. It was really inspiring to me when I first went there.
Hey, Jake, it's Bob.
Yeah.
I think Lori's class has to
they have to go
leave soon, and they're anxious to see that demo. So
Okay.
if you
Well,
and
we'll do 'em
Thug
very
or can get together, let's do that demo.
Well, let's do some demos. And these are kind of challenges. But the first one I want to do is one I hadn't planned. I did it the other day, I think. So let's see if so the young lady that asked about getting oxygen, and this I've got some activities I want you to do in your classroom. So we did this the other day, but I thought I'd repeat it for this group. So we're going to generate some oxygen and hydrogen.
We're going to make oxygen here.
Oxygen and hydrogen right here in the studio. Now I've got a beaker of water. Are you on that, Jacob? Zoom down on there. There's a beaker of water. Okay, let me turn that. Get those. Yeah, there we go. There you go. That's just plain old tap water, and I've got a 9-volt battery. Right there it is. So you could do this in your classroom if you want to. I'm going to take the cap off here. And I just put this washer on the bottom to make it more stable. Are you with me so far?
I'm there with you.
Okay, 9-volt battery, beaker of water. And I'm just going to lower the battery into the water. There it is. See that? With me so far? And I'm going to take a little salt. Here's salt shaker right there. And this is just an electrolysis experiment. I just put a few drops of salt. And that I just did a little second. Now let's zoom in on that, Jacob. Is that pretty tight? Oh, do you see what's coming off of the poles of the cell, or the battery? I've got, let's see, right there, on this side. Oh, that isn't going to work. There we go. Oh, I see a little stream of bubbles coming up. And it looks over on the other side, I see a little larger, about twice the size stream of bubbles coming up. And what's the formula for water?
Well, it'd be 1 part hydrogen.
Yeah.
No.
2 parts hydrogen. H2O.
One
H2O.
oxygen.
Yeah, 1 oxygen. So I wonder if it's H2O, which stream is which? We're separating the hydrogen from which one do you think? I'm not going to answer it. Let you guys figure it out. And the challenge I'll have you do is to see if you can catch some of that hydrogen and catch some of that oxygen. You're going to have to figure out your own technique for catching it. But we're doing a simple separation here. And instead of having a fancy Hoffman apparatus to do that, or a fuel cell as they might have in outer space, we just did it with a glass of water and a 9-volt battery. And that pretty much ruins the battery, but that's okay.
Yeah, well, the object is to get the hydrogen and oxygen.
Hydrogen and oxygen, that's one way to separate it. So if I ever go to outer space, if I don't go crazy from, I want to know who finds out if the urine recycler is not working. Oh. That's let Kevin do that job.
Yeah.
Taste that water. No, that's
Kevin's
not.
got form at drinking urine actually, so maybe he should be first volunteer.
Oh yeah, that's right. Kevin did drink the urine water, didn't he? That I saw that.
Yep. It tasted pretty much like urine after it had been filtered.
After it had been filtered, did it taste? I'm not even going to go there. No, not going there. No, I'm not going anywhere near that. So here's a couple more activities you can do right there in the classroom. These are little challenges. Now you notice I've got a couple of cans right here, and these are official science cans. You don't have to have anything like that. But Kevin talked about how in outer space they have to either add heat to the spacesuit if you're cold or get rid of the heat if you're overheating, right?
Yeah.
So there's a basic bit of science that I know you already know the first half of this. So here's the sun right here. I captured some sun and put it inside this lamp. Do you believe this?
Yeah, well, I saw you do it. It was difficult.
It was difficult, but I got a sun lamp there. And here is a black can and a silver can. And if you've ever worn a black t-shirt outside or a white t-shirt outside, you know one of them's going to heat up faster.
Yeah.
Right. And you could do this. You could find a couple of cans and paint them, or if you just get some black tape and some white tape and wrap something up, you could do an activity and set them out in the sunlight and see, and what would you predict? Which one of these is going to get warmer faster?
Well, I think the black one is going to get warm.
Well, we all know this because it absorbs the energy, right? I mean, it absorbs it more, and this reflects more of the energy. But the question I want to put to you is, when I turn the lights off, everybody, oh, the black one got warmer faster, right? Because it's absorbing more. This is reflecting more energy. Yeah. But, and I don't yell the answer out because you might not know. Yeah, you might not know. When I turn the light off, are they going to cool off at the same rate? We know they cool off. So does one of them cool off more faster than the other? And if it does, which one?
That's a good question.
That's a good one. And I want you to predict, before you do it, I want you to test, which one do you think is going to cool off faster? Is it the same as when one of them heated up faster, warmed up faster? Wonder which one would cool off faster. I know that. You're going to have to find that out. And here's another activity you can do. Talk about transferring heat. I love this one.
Oh, yeah.
This is a good one. This is a good one. So that's a good one. So all you need to do is get a big fat rubber band or a balloon like this. So you get everybody in the class a rubber band or a balloon. And I don't have thermometers for everybody, but I know Kevin can validate this, that we have four different types of nerve endings. We got pressure and heat and cold, and you got, I don't know, 3 or 4 different types of nerve endings on your skin. And right down here through the front of your face, I know you've got a lot of nerves that come around like this. Right down through, very sensitive. A lot of nerve endings right here. Yeah. So I want to take this balloon or rubber band and put it right here, or put it up on your forehead like this. Okay, and see if you can kind of tell the temperature. And then, this is about room temperature. Yeah, yeah. I can feel the heat right here, or lack of heat, whatever the room is. That's about the same temperature. Now I'm going to take this balloon, and I'm going to stretch it as far as I can without snapping my neighbor next to him. I'm going to stretch it and touch it to my forehead, and I will notice something. I'm going to notice, ooh, I feel something. I feel something.
What do you feel?
What do I feel? Well, I'm going to have everybody do that in school. And actually, I'll just tell you the answer, and you will feel it. It feels very warm when I stretch it. Very warm when I stretch it. Now, the question is, where's that heat coming from? Yeah, I got to think about this. No answer yet. Because right now I don't feel the heat. Now all of a sudden, I've got, oh, it's really warm. Wow, I can feel the heat leaving the balloon and going into my head. Now what would be, I want you to think like a scientist, what would be the opposite of heat leaving the balloon and going into my head? What would be the opposite of that? And what would be the opposite of stretching the balloon? What would that be?
Would that be letting the balloon
go back? Yeah, contracting. Back. So I want you to think like a scientist. If I feel heat leaving the balloon, and I put it up there, what am I going to feel when I let it go back together? Wow, that is incredible. Pull here. That's incredible right there. That's even more incredible. Whoop. And if you do this simultaneously, you can make your whole class look silly at the same time. But believe it or not, I know one of the problems that the NASA folks have is how they transfer.
I have to go. I'm sorry. Thank you. Bye.
Bye. Well, you guys do those. You try those activities. Thank you, Barrett. They got to go to class. They're out of there. They're running out.
They
had to get to class. I talk too much. Well, anyway, there are some activities you can do, and this particular one is, I know in space, the astronaut, one of my friends, Mike Massimino, talked about this. He said, getting rid of heat or saving heat, moving heat about in space is an issue. Either I got to get rid of it real quick, or I don't want it to come this way, or I want it to go this way, and that sort of thing. So this is just an activity that you can do with balloons or rubber bands to see that, yes, we can manipulate things and move heat about one place to another. A little thermodynamics activity. Are you still there, Bob? I think it's about time for us to go. So we'll say goodbye. Let's say goodbye to the folks in England.
Got about 60 seconds.
Okay, hey England, are you still there? UK and Yorkshire. Hey, all right. Hey, you try some of these activities, and we'll connect again and do some more activities. How about that? Yes. Hey, it was nice to meet you all. Thanks for stopping by our hangout. We'll have some more hangouts. And let's go back to the other school. Hey, what I'm saying. Let's go to the other school. Is it still on? Still up? Is Wiley still around?
Hello.
Hello. Hey, thank you, folks, for stopping by.
Thank you, Wizard.
Hey, you're welcome. I want to come back to your school. Bye. We're going to come back to your school. Well, thank you, Kevin. And thank you, Joya and Trent and Karen and Ollie. Thank all of you for this fine activity. This was great fun. I hope we can do it again. Yeah. So everybody say goodbye. Swing around, Bob, and have them all say goodbye.
Bye.
Bye, Kevin.
Bye, guys. Bye.
Hi, Kevin.
All right. Thank you, Kevin.
Bye.
Thank you, Trent and Joya. Thank you. You're good people. Good people all.
Allegedly.
Allegedly. Sweet potatoes. See you, sweet tater. And Ollie. Oh, we forgot to have Karen do her pitch.
Bye.
Bye, Ollie. Thank you.
Thank you.
You're a good person in spite of what we hear to the contrary. And Karen, are you there?
Karen can't get back in, so I think we're
Okay.
out of time. We'll have to get her back on sometime.
All right. Thank you all. We'll see you next time. Bye.